Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at finite difference methods for boundary value problems. So in this topic we will describe finite difference approximations of linear ordinary differential equations. We will see how this can be used to approximate solutions to boundary value problems. We will observe that this defines a system of linear equations, that is, one that we can already solve. And we will look at examples both with constant coefficients and with variable coefficients. We will also look at examples and describe implementations of solvers in MATLAB. Now in this topic, we will focus on a technique appropriate for linear ordinary differential equations. Now the most general form of such an LOED is a linear combination of u and its derivatives. And it's of course important to remember that the coefficients, including the right-hand side, can actually be functions of x. So that's subtly different from what you have seen in your linear algebra courses, where the coefficients must be constant. Now, in your calculus course, you actually did focus on finding solutions to linear ODEs with constant coefficients. However, the approximation techniques we will see here will generalize to allow us to solve much more general, or correctly, approximate solutions to much more general second-order linear ODEs. Now, this linear ODE, which is second order, has both a derivative and a second derivative. And you will recall previously we saw two divided difference approximations of these derivatives, both of which incidentally are order h squared. Now I'm going to write the derivative as negative u at x minus h plus u at x plus h, while the second derivative is approximated by the combination u at x minus h minus twice u at x plus u at x plus h. Again, over the appropriate denominator. Well, we have an ordinary differential equation here. How about substituting in these two approximations into this equation? Thus, we go from the linear second order differential equation and substituting the approximation of the derivative and the approximation of the second derivative. This goes to this expression here. Okay, it doesn't look like we've made life any easier. However, so let's expand this, but we're going to now collect on the terms u at x minus h, u at x, and u at x plus h. Okay, so expanding that out and collecting, we get this expression here. So now we have u at x minus h times some expression depending on the coefficients, plus u at x times another expression, plus u at x plus h times yet another expression, all approximately equaling g at x. Finally, to simplify this expression, let's just multiply both sides by the common denominator of 2h squared. All right, so now we have a little bit simpler expression that gives an approximation, a finite difference approximation of the original ordinary differential equation. So if a solution to the ordinary differential equation exists, then this statement must be approximately equal to. Whereas on the other hand, if we find a solution that satisfies this one, then hopefully it will be close to the solution to the ordinary differential equation. To reiterate, if u at x satisfies this linear ordinary differential equation, then it must also be true that this expression must be approximately true. It may not be exact because we have substituted in approximations, but it should be very close. Now, let's take a look at this problem visually. Here we have the ODE and the two boundary conditions shown here visually. Now, there is an actual solution that passes through these, or at least we're assuming that there is such a solution. How are we going to approximate this solution? Well, first of all, take the interval from A to B and let's break that interval into n equal subintervals. Well, if this is true, then each of these subintervals will be of width h, which is b minus a all over n. Consequently, if we were to denote the kth point, endpoint of these subintervals as a plus k times h, consequently this would mean that x naught would be a and xn would be b. So here we see, for example, the case where n is equal to 10. There are 11 points as there are 10 subintervals. The width of each subinterval is b minus a over 10. Consequently, we'd like to therefore say, for example, approximate the value of the solution to the boundary value problem at x1, or alternatively, approximate the solution at x6. Now, for a more general n, let's now focus on a single point x sub k. Now, we don't know what the value of the solution at x sub k is, but we know that the equation we see here should be approximately true. Consequently, what we will do is we will represent our estimate of the solution u at x sub k with an unknown u sub k. So consequently, u sub k is approximately u at x sub k, where again u is the actual solution. All right, note that xk minus h is just xk minus 1, and xk plus h is the next x value, xk plus 1. Consequently, u at x sub k minus h is just the same as u at x sub k minus 1, and we are approximating this point by an unknown u sub k minus 1. Similarly, u at x sub k plus h is just u at x sub k plus 1. And again, we are approximating this point by an unknown u sub k plus 1. So what's interesting here is even though this finite difference equation looks really ugly, remember that the four functions a2, a1, and a0, as well as g, are known. Also, h is known. Consequently, all four values are known. Essentially, what we have here is a linear equation in three unknowns. The three unknowns being u sub k minus 1, u sub k, and u sub k plus 1. The coefficients, we already know what they are because we can calculate them because they are given in the boundary value problem. Specifically, p sub k is just twice the function a2 evaluated at x sub k minus the function a1 evaluated at x sub k times h. Similarly, q sub k is the corresponding coefficient evaluated at x sub k, and r sub k is the corresponding coefficient evaluated at, again, x sub k. Of course, we have the right-hand side that is also evaluated at x sub k, where we evaluate the forcing function g at that point. All right, so for each of the unknowns u sub 1 through u sub n minus 1, we can write down such a linear equation. So for example, when k is equal to 1, we have this linear equation in u0, u1, and u2. When k is equal to 2, we have a linear equation in u1, u2, and u3. When k is equal to 3, we have a linear equation in u2, u3, and u4. Same with u when k is equal to 4, and we can do so all the way up to n minus 2, and finally with k equaling n minus 1. As you can see, this gives us n minus 1 equations in n plus 1 unknowns u0 through un. Now normally, having fewer equations and unknowns would be the end of a story, because if there is one solution to such an underdetermined system of linear equations, there must be infinitely many solutions. However, we're lucky here, because you'll remember that u sub naught is the unknown function u evaluated at x naught. But x naught is equal to a, and u at a is given in the boundary condition as being equal to u sub a. Thus, u sub naught is not an unknown. It is the value in the boundary condition u sub a. Similarly, u sub n is the approximation of the solution at the point x sub n, but x sub n is equal to b, the other endpoint of the interval. And u at b is given in the boundary condition as being the given value u sub b. Thus, u sub n is given, and its value is equal to the value u sub b. Thus, equations 1 and equations n minus 1 have values u0 and un that are actually known, and thus they can be modified. So the first equation has u0 equaling u sub a, but u sub a is a known value, and therefore we can move it to the right-hand side. Thus we now have a linear equation in two unknowns u1 and u2. Similarly, the last equation has u sub n being given as the value u sub b. Well, that is also a known value, and therefore we can move that also to the right-hand side of the linear equation. Thus, the last equation is now a linear equation in only two unknowns, u sub n minus 2 and u sub n minus 1. Thus, we have the following system of n minus 1 linear equations in n minus 1 unknowns. You will notice that the only non-zero entries of the matrix are on the diagonal, the superdiagonal, and the subdiagonal. Consequently, this is described as being a tridiagonal matrix. Now, there's something actually really nice about a tridiagonal matrix. Such a system of linear equations can be solved using Gaussian elimination and backward substitution in order n time and not order n cubed time. So it's actually very efficient to find such solutions very quickly. Now suppose we have a linear ODE with constant coefficients. Well, in this case, a2, a1, and a0 are therefore constant and not dependent on x. Consequently, the matrix entries are always identical regardless of which row we are on. P, Q, and R are unchanged throughout the matrix. Thus, our matrix becomes greatly simplified. All the entries on the diagonal are the same, all the entries on the superdiagonal and on the subdiagonal are equal. Now, we will first look at an implementation of and an example of a boundary value problem with constant coefficients. That is, again, A2, A1, and A0 are fixed real values. Next, we will look at an implementation of and an example of a boundary value problem with variable coefficients, that is, where A2, A1, and A0 may be functions of x. All right, let's look at an implementation of a boundary value problem solver for constant coefficients. The first argument is a vector of 3 entries: the coefficient of the second derivative, the coefficient of the derivative, and the coefficient of u of x. The second parameter is the forcing function. This is assumed to be a function of x. The third parameter is the x range, that is the interval from a to b, and this is represented by a two-dimensional vector. The next parameter is a vector of 2 entries, which once again represent the boundary value at both the left and right endpoints. So u at A and u at B respectively. The third argument is the number of intervals into which the x range will be broken into. So first we calculate h, which is the width of the interval divided by n. Next, we calculate the 3 coefficients, p, q, and r. So again, ODE1 is the coefficient of the second derivative, ODE2 is the coefficient of the derivative, and ODE3 is the coefficient of u of x. Now we can create our matrix. So we have 3 separate matrices we are adding, and because we're adding these on separate lines, then we have to put ... to indicate to MATLAB that the line continues to the next line. Now, the first one has 1s. That creates an n-1 by 1 matrix, which is essentially an n-1 dimensional column vector of 1s, and this is scalar multiplied by q. So this creates a vector of n-1 q values. We pass this on to diag, and this creates a diagonal matrix with those n-1 entries on the diagonal. Of course, the result is an n-1 by n-1 matrix. Next, we create an n-2 dimensional vector of our values, and we call diag, but we call it with the argument 1. So this creates an n-1 by n-1 matrix that has the n-2 r values on the upper or super diagonal. Because remember, a 10 by 10 matrix has 10 entries on the diagonal, but only 9 entries on the super diagonal, as well as 9 entries on the subdiagonal. The last statement creates a matrix that has n-2 entries on the subdiagonal assigned to P. Adding these two together gives us our matrix. Next, we're going to create a vector of x values ranging from a plus h to b minus h with n-1 points. So this essentially will be the values a plus h, a plus 2h, a plus 3h, and so on and so forth up until b minus 2h and then b minus h. These are the n-1 intermediate x values. Now, linspace happens to return a row vector, and so we create a column vector by taking the transpose by adding an apostrophe at the end of the statement. We now create the right-hand vector v, by evaluating the forcing function at each of the x values and multiplying each of these by 2 times h squared. However, you'll remember that we must update the first entry of the target vector by subtracting off p times the left-hand boundary value, and we must update the last entry to subtract off r times the right-hand boundary value. Okay, having done so, we can solve for the u values simply by solving the system of linear equations. What we're going to do now is we're going to add a and b onto the vector of x values, and we will add the two boundary values onto the u vector. So consequently, this returns all the x values from a to b and the approximations or exact values at the endpoints of all of these x values as well for the returned argument us. Now, suppose we have the following boundary value problem with constant coefficients, the coefficients being 1, 3, and 2. The forcing function is sine of x, and the boundary conditions are that u at -1 is equal to 1, and u at 1 is equal to 2. Now, if n is equal to 10, then h is equal to 0.2. So consequently, we may determine that p, q, and r are these expressions. We can substitute a2, a1, and a0 as well as h into these expressions to get these three, which then give us that p, q, and r for this particular ODE are 1.4, -3.84, and 2.6. Also, the x values are -1 through 1 by increments of 0.2. So -1, -0.8, -0.6, and so on and so forth up until x equals 1, the right-hand boundary point. Thus, we have our system of linear equations where we are approximating the value of the solution at x1 through xn-1, in this case x1 through x9. And of course, the approximations are the values u1 through u9, which we will attempt to find. Now, here we have p, and p occupies each of the entries of the subdiagonal. Here's the entry q, and it appears on the diagonal, and the entry r, which appears on the superdiagonal. In the right-hand vector, there we see twice the forcing function evaluated at each of the x values from x1 through x9 times h squared, which in this case is 0.04. Additionally, we had to subtract off p times the left-hand boundary value, which was 1. And here we had to subtract off r times the right-hand boundary value, which in this case was 2. Solving this system of linear equations yields the following vector. So, for example, the first entry is our approximation of u at -0.8. This entry is our approximation of u at 0.4. Now in MATLAB, we can call this solver boundary value problem with constant coefficients, where the first vector are the constant coefficients of the second derivative, the first derivative, and the unknown function u of x. The second is the forcing function, which in this case is simply sine. And then we have the boundary, or the endpoints a and b, -1 and 1, and the boundary values in this case, u at -1 was 1 and u at 1 was 2. We're splitting up the interval into 10 points. Next, we are actually going to look at or be able to plot a function u, which is to 16 significant digits the actual solution. This is found with a symbolic computation package like what you find in Maple. So this is the to 16 significant digits, the exact solution. So we could plot both the points that were returned by the boundary value problem with constant coefficients function, and we can also plot the actual solution. So here is a plot of the solution in red and our 9 approximations going from -0.8 up to 0.8 in the interior, and we can see it's not unreasonable. Again, this isn't very many points, and so it's not great, but we could get better precision by using more subintervals, which would give us a better approximation. Now let's look at a function that will find an approximation to a solution to a boundary value problem when the coefficients may actually be functions of x. Now, unfortunately, in this case, it's very difficult in MATLAB to have an array of function pointers, and therefore instead we will just simply have 3 parameters, a2, a1, and a0, which are the functions that are the coefficients of the second derivative, the derivative, and the unknown function u of x. First, we'll calculate the h value, which is b minus a over n. Now, at this point, p, q, and r actually depend on x. And so what we're going to do is we are going to define p, q, r, and r as functions of x, where, for example, p at x will evaluate to twice whatever a2 evaluated at x is minus a1 evaluated at x times h. So now what we will do is we will pass different values of x to p, and that is what we will use to populate the matrix A. Here we have a Lin space, so this creates n minus 1 points going from a plus h all the way up to b minus h. These are the points at which we will find or approximate the value of the solution. Once again, the apostrophe at the end converts a row vector into a column vector. So now we're going to create our matrix. We're going to create a matrix that is n minus 1 by n minus 1, and we'll just initialize it with all zeros. What we will do now is we will go along each of the diagonal entries and we will evaluate q at the corresponding x value. And then we will assign each of these. We now have to populate both the superdiagonal and the subdiagonal. And you will note that we are always evaluating the corresponding function relative to the row. So in the second row, we always ensure that we are dealing with the second unknown x value. To finish, we just create the right-hand vector. And then once again, as before, we have to update the first and last entries to deal with the fact that we have the 2 boundary values. So here we update the first entry by evaluating p at the first x value times the left-hand boundary condition. And here we're updating the last entry of the target vector by subtracting off the function r evaluated at the last x value multiplied by the second boundary condition. We then solve the system add the first and last points A and B, and then add the two boundary conditions on either side of the resulting output vector. Okay, and we're done. So suppose we have the following boundary value problem. It looks similar to the previous boundary value problem. The forcing function is the same, the boundary conditions are the same, but now the coefficient of the second derivative is a function, 13 times x squared. The coefficient of the derivative is -5, and the coefficient of u of x is 8 times x. So now the coefficients are to be treated as functions of x. Once again, if n is equal to 10, then h is equal to 0.2. So now p sub k is the entry twice the first function evaluated at x sub k minus the second function evaluated at x sub k, all times h, and so on and so forth for q and r. And we can now substitute these functions to give these expressions. As before, the x values are -1, -0.8, -0.6, and so on and so forth up until 1. So if we now evaluate the functions p, q, and r at the various x values, we populate the matrix as we see here, at least to 1 decimal point. Clearly, the computer would store much more than this, but I'm just using this as an example. So for example, p evaluated at the second unknown or x value at which we will approximate the solution is 10.4. Q evaluated at x2 is -19.1, and R evaluated at x2 is 8.4. The right-hand side is the same. We've evaluated the forcing function at each of the interior x values from -0.8 all the way up to 0.8, and we have multiplied each of them by 2 times h squared. We then subtract p evaluated at the first point, -0.8, times the left-hand boundary condition, which is 1, and we subtract from here r evaluated at the last x value, in this case 0.8, multiplied by the second boundary condition, which is 2. Solving this system of linear equations yields these points, and so, for example, the fourth entry is the approximation of the solution at x equals -0.2, and that last entry is our approximation of the solution at 0.8. Now here is a plot of the actual solution and our approximations at the points going from -0.8 all the way up to 0.8, and you can see it's not ideal, but it's not unreasonable either. And making h smaller, that is, including more points, would give us a better approximation. And given the fact that we only have 9 points, this isn't actually that bad. Now, one interesting point is there is no algebraic expression that gives us the exact solution. So what I am drawing here as a red line is simply a much more accurate approximation than the one that we are using with our technique. We can also use more points. So for example, if we were to break the interval -1, 1 into 200 subintervals, so h is equal to 0.01, we get a much better approximation. This is shown by this image here, where we have 201 points versus the 11 points shown in black. Again, The actual solution is shown as a red line, and if you look carefully, you can see that the red line more or less perfectly follows the centers of the circles representing the 201 approximations. Now, beyond the scope of this course, you may be thinking now, wait a second, we are using 2 order h squared approximations of the derivative and the second derivative. So when we were doing the composite trapezoidal rule or approximating solutions to initial value problems, if we started with an operation that was order h to the n, then repeated applications would result in an error that was of order h to the n minus 1. However, in this case, because we are solving all of these simultaneously and as each of the solutions depends on the others, the overall error of this method is still order h squared. Consequently, if we double the number of intervals, this is going to reduce the error by a factor of 4. Following this topic, you now understand the idea of a finite difference approximation. Specifically for a linear ODE, we substitute approximations of the derivative and the second derivative. This gives us our finite difference equation. We know that this equation defines a system of linear equations. You understand that the solution to this system of linear equations gives approximations at the equally spaced points between the endpoints A and B. You are aware that if the linear ODE has constant coefficients, all the entries on the diagonal, the superdiagonal, and the subdiagonal are equal, respectively. And you have seen an implementation of solvers in MATLAB. Acknowledgements, the colophon, and a disclaimer. Cheers!